This is the screencast for section 3.1, example 6. When a function is differentiable on a closed interval, so from an x value a to another x value b, it has a derivative at every interior point. Okay, wait a second. A derivative at every interior point means that the limit as h approaches 0 from the left of the differential quotient equals the limit as h approaches 0 from the right of the differential quotient. So kind of like a function being continuous or having a limit. The limit of the slopes from the left and from the right have to approach the same value. It has to be kind of smooth in there, so there's an obvious slope of the tangent at that point. All right, so again, for a function to be differentiable on the closed interval, it has to have a derivative at every interior point, and the limits exist at the endpoints. So we have, much like continuous and having a limit, differentiable from the right, or differentiable as a left endpoint as h approaches 0 coming in from the right here. Or we can have a point that is differential from the left, or differential as a right endpoint, a left-hand derivative, over here, assuming that the limit as h approaches 0 from the left has a slope. Now this information is going to be used in different situations. In this example here, we're going to show that a function has a left-hand and a right-hand derivative, but no derivative. So in other words, we're going to show that an interior point does not have a derivative. So in example 6, I'm going to start by drawing this piecewise function, and then I'm going to show that it has a left-hand derivative and a right-hand derivative at x equals 0, but the derivative itself, so the two-sided derivative, does not exist. First, I'm going to draw the piecewise function, and as you can see, there's this little pointy spot there where it's going to be kind of unclear where the derivative goes and what slope that's going to take on. It's not really smooth, so do you have the slope 2, like the rest of this line on the right? Or do you have a slope 0 as it's meeting a minimum here of y equals x squared in a horizontal tangent line? So because there's a big question mark, there's going to be no derivative, but we got to show that. So let's look at the right-hand derivative. We want to know specifically what's happening here at x equals 0. So coming in from the right towards x equals 0, I'm looking at the piece 2x. So I want to know the limit as h approaches 0 from the right of f of x plus h, so that's 2x plus h, minus f of x, so 2x, all over h. And then I can distribute the 2 and simplify and take the limit, I'm going to cancel out the two h's, and I get 2. So the slope coming in from the right towards 0 is 2, which you already knew that because it's a line of slope 2. Now looking at the left-hand derivative, so coming in from the left, we're looking at the derivative of this piece as a right endpoint of this piece. The limit as h approaches 0 then from the left-hand derivative, is going to be f of x plus h, so that's x plus h squared, minus f of x, so just plain old x squared, all over h. So I'm going to distribute out my x plus h squared. I'm going to still approach 0 from the left. Now my x squareds cancel out, and then I simplified with by dividing everything by an h, and I'm still approaching 0 from the left. So now if I plug in 0 for h, because I'm looking at the limit as h approaches 0, I'm also looking for the point where x equals 0. So I get the slope coming in from the left equals 0, and we knew that because this is a minimum. It would look like it was going to be about a horizontal tangent. So the left-hand derivative exists, the right-hand derivative exists. However, the derivative does not exist at x equals 0 because the limit of the slopes, the limit as h approaches 0 from the left of our differential quotient, does not equal the limit of our slopes from the right, the limit as h approaches 0 from the right of our differential quotient. For the now try problem number 31, I'm just going to dive right into this problem. I'm going to look at the left-hand derivative. So the limit as h approaches 0 from the left. So we are looking at an x boundary of 1, but I still want the distance between these 2 points to be 0. if h is approaching 0 from the left, that means I'm going to be looking at x values that are less than 1. And then the piece I will use is x squared plus x. So f of x plus h is x plus h squared plus x plus h. And then f of x is x squared plus x. So now I multiplied a lot of stuff out, distributed the negative, combine like terms, simplify an h out from every piece of the numerator and the denominator. And all along here I'm looking for the limit as h approaches 0 from the left. So now I can take that limit and I get 2x plus 1. Well, the x value that I'm looking to find the slope at is at x equals 1. So 2 times 1 plus 1 is 3. So the slope is 3. Okay? Now let's look at the right-hand derivative. The right-hand derivative is going to use the other piece coming in from the right at x is greater than 1. We have f of x plus h, so that's going to be 3 times x plus h minus 2, minus, and then just f of x, so 3x minus 2. Distribute the negative, distribute the 3, combine like terms, simplify the h out, and all along it's the right-hand derivative, so I'm looking at the limit as h approaches 0 from the right. But that just simplifies out and I get that the slope is 3. So I can easily make my conclusion that the derivative exists. But wait, hold the phone. Does it exist? Let's graph it to make sure. So I'm going to graph my piecewise function. So on the right side I have the piece y equals 3x minus 2, and on the left side you see the piece y equals x squared plus x, and they don't line up. They're not continuous. If I plug in 1 to the left piece, I get out 2. But if I plug in 1 to the right piece, I only get out 1. So in this case, the limit as h approaches 0 from the left does equal the limit as h approaches 0 from the right. So in this case, the limit of the slopes from the left and the right are 3. The tangent of both of these pieces is going to have a slope of 3. So the limit of their slopes is the same. However, the limit as h approaches 0 from the left of the actual function, so the y values coming in from the left, do not equal the y values coming in from the right of just the actual function, not f of x plus h, not the difference quotient. The actual function's values aren't equal. Therefore, f of x is not continuous at x equals 1, so it is also not differentiable. Now you're probably asking yourself, couldn't I have just graphed that and shown that right off the bat and not gone through all that? Well, no, because the directions said that you had to use one-sided derivatives. So you did. You used one-sided derivatives, and those are actually equal, but then you had to make the conclusion that because it was not continuous, it's also not differentiable.